Okay, we're on air. Oops. Hi, everyone. So today, the goal is to have a little fun and not get intimidated by the title of this presentation, Best Ideas of 2021. But we all read lots of papers in 2021. We all discussed papers here by themselves. So the idea is each of us would add a slide and with an idea that we learned about in 2021, potentially published in 2021, but okay, and it doesn't have to be the best idea because it's very hard to evaluate what's best. Best is ill-defined. So whatever you like, you posted a slide and we'll discuss today, each one of us present or whoever put a slide, and let's have fun. Let's go on. So we have, well, for a while, this is potentially our new logo designed by Farfalla here, who's in this room with us. A new student. Can you wait there?
Hello.
Yeah. So some brain ice cream. But this presentation was shared. This presentation was shared very long ago, and nobody added a single slide. So Harsh got on, and he left that comment. No more ML research.
Oh, no, that's me.
Oh, was it you? Yeah, I thought I blame Harsh for anything like that. Yeah, that's a sweet logo. First comment from teacher. Yeah, so he's done that, but I guess when we'll be eating brains like that, no more ML research, at least for this sugar brain. So let's go on with presentation. Best idea of 2021, number one.
Oh, wow. Yeah, I don't know. Best idea is an overstatement, but I think this is really interesting. Because what they're doing here is they're saying why convolutional neural networks don't have any topographic information. Like you can see AlexNet on the left. It's like a activation map. It's fairly random. And obviously you can learn to classify objects, but the brain, we know certain neurons are highly selective for certain things, objects, and that selectiveness is topographic. So for AlexNet, you can see that neurons are kind of randomly distributed throughout the feature, like the activation map, what they are being activated for, which is fine because it doesn't, for AlexNet, it doesn't really matter because it can still find the correct neurons to connect to do a correct classification, basically. But this paper is basically saying that's how the brain works, and let's see if we can make something that is topographic. And so there's been work before like TDAN, but they're using something that's called a topographic VAE, and they show that it becomes way more. It has more of a topographic structure in the activation map and what it's selected for, which I personally thought was very interesting. And you can see it's different for how deep, the deeper you go in the network. So I thought that was really cool. It's very new work by Welling's group in Amsterdam. And they also found that topographic VAEs can learn equivariant capsules. And what they basically do is they add a terminal loss that makes sort of close things together more similar. So I thought this was cool because it's maybe interesting to think about that, although convolutional neural networks are obviously doing well and transformers and whatever, if we really want to make it more efficient, maybe going this route is a good idea because it resembles the natural basis that we have for how it can be more efficient. Object detection is what I'm talking about. So I thought this was interesting. I think it's always good to ground neural network research in the brain. And this one stood out to me, partly also because the figures are very beautiful.
So is there any reason that why AlexNet is doing correct classification instead of having uniform, not understandable?
So, I mean, it doesn't matter for AlexNet, right? It doesn't have to do, the brain needs to do minimized wiring. But AlexNet, I mean, it doesn't really matter if two neurons that are next to each other in AlexNet have the same feature that they're selected for, because they're not connected to each other within a layer. So it's only top down. But in the brain, there is the connection between neurons in a layer. And it's a very important connection in fact, it's one of the most important ones, because the term is like, it needs to be, you want to minimize wiring. So if two neurons that are next to each other in a layer are not selected for the same thing, they're going to interfere with each other. But if with AlexNet, it doesn't matter, because like it just needs to be correct. It needs to be corrected to it needs to be connected to the correct one in the bottom, which it still can do, because there's blue, orange ones, and that orange one, for example, let's say in the top left, can still be connected to the correct one in the next layer. Like that doesn't matter for the classification, but in terms of like how much it represents the actual brain, you need to take into account that sort of like within layer connection.
So your own, that may be interesting for you. It's like going from introducing dependence between slices.
Yeah,
Just maybe you want to look at this later when you.
yes, I'll think about.
It's also interesting because what they do, for example, this is being done also in Bayesian neural networks specifically, because there you want to. But I think this one, they have a much more simpler and more elegant sort of solution to it. It's like they don't add specific dependencies between neurons. They just add like an extra loss where they say it needs to be like homeomorphic or something.
No, this is like Markov random field. That's probably what you mean in Bayesian networks, right?
Yeah, well, there they specifically make the connections. Here they don't specifically connect the neurons or say like, oh, these need to be per se the same, but it comes from an extra loss term that they become more similar. So I thought that was kind of beautiful. I don't think this actually explains the brain or whatever, but I think it is cool to think about these things like, hey, you know, people always say like, oh yeah, V1 and whatever, it looks like convolutional neural networks. Partly true, but there's still a lot more that the brain does that we are not incorporating in these neural networks. And it's cool to think about like how we can, and maybe that'll also make them more like efficient in terms of data use.
But they basically presented the idea. They didn't like beat state of the art or things like that.
No, but I think that's also not their point. I think their point was more to show like, hey, with this simple additional loss, you already get much better topographic. I think, you know, I don't think state-of-the-art beating is what we're looking for per se always. I think grounding it in what we know about the brain is also a very valid result. Like, hey, this is more like what we can do, what we do in the brain.
Where is it published?
I don't know, probably nerds or something. I think I'm not even sure if it's published yet because it's very recent, but knowing Welling's group is probably at like a conference or a CS conference.
Oh, that's from Welling's group.
Yeah.
Okay, should I move on to the next? MLB?
So MLP mixers, right? So this is came out early 2021, like I think it came out in like the spring, and it's been part of this, I think, new wave of counter CNN based sort of work in computer vision, which is certainly useful for a lot of different reasons. If you're like me, we have new methods which don't work well for CNNs, for example, but the complexity of CNNs is just generally something that people tend to be reckoning with. So these, this work is showing, right, that we can, with some sort of clever configuration of multi-layer perceptrons, ultimately just linear layers, we can get results that are on pair in computer vision with CNN-based architectures. The general idea is kind of similar to visual transformers, at least in the input, right? We're kind of breaking up our input into patches, feeding it into our network, and then doing this, having NLPs within the architecture that actually mix information between the channels, between the sort of spatial regions within the image. So we sort of get this sort of same spatial mixing and channel mixing that we get for convolutional layers, but entirely with a linear architecture. So it's relatively straightforward, right? But it's like using these sort of very straightforward networks in kind of clever new architectural ways to get around these sort of the complexity of convolutions. And I just think that's always like really beautiful when you can go back to these very simple methods and just kind of connect them in new and different ways. Looking at your input in different ways and looking at how your architecture is organized in different ways, and coming up with results that are challenging sort of our state of the art. So I think we'll probably have other people talking about visual transformers, but the MLP mixers I think are a cool sort of step in the direction of for computer vision for MLP sort of primary architectures.
I think it's funny because there was actually a paper after this, I think a few months, which is called Conv Mixer, which was even better. And it replaced the MLPs again with convolutions, but just made the kernels really big. And then it was even better.
But there is
Yeah, I
also,
mean, the idea of mixing inputs, or mixing sort of parts in your embeddings in your architecture is itself, I think, interesting, right? And that's sort of maybe the core contribution of this work, right? Maybe not that NLPs by themselves are particularly special, but the idea of having architectures where you have these sort of mixer modules is itself seems to be kind of interesting and useful, whether you have convolutions or MLPs as sort of your kernel.
Right. In that paper, they specifically said patches is all you need, as in they attributed the high performance also to the fact that you have patches. And that helps with that mixing that you also talk. I think this one is really nice because I agree that it's good to have a model that performs just as well, where you don't have to per se do convolutions.
but there is even more recent paper from Fair, or I don't know what they call it now. Facebook
Next.
Yeah, Conv Next, where they say just convolutions, just 3x3.
Yeah, no.
Fine,
Yeah.
beats them all. Well, with some tricks and stuff, but still CNN is powerful inductive bias.
Right.
And I think we're seeing it's becoming kind of a polemic here in the community, right? Like what sort of base architecture is the most useful. And I'm increasingly convinced that we're probably not going to come up with a consensus, right? It's ultimately going to depend on these sort of higher level architectural organizations, these modules that people build, and how people work with the inputs.
But Walpert already proved it in the 70s, the series of papers called No Free Lunch Steerings. We will not have a consensus because there are no single architecture that rules them all. Different problems demand different approaches.
Right.
So
And
it just makes
one
no sense.
thing with ConvNext was that a lot of people are saying, well, I mean, they also just use very new, cool ways of like training it, which may also improve the performance outside of the architecture one, right? There was like on Twitter, there was like a
Well, they said
discussion.
let's replace their point is let's replace every architectural decisions and leave every new training decisions and see, because the claims are about convolution. They don't hold.
Right.
It's other things that improve the architecture.
Right, that's what,
You know, one veggie, one meat. Yeah. Thanks. Okay, thank you, Brad. Yeah, that's indeed an interesting paper.
I think this is also awesome for neuroimaging in general, because we may not want to do convolutions for the brain sometimes, like activations in some part of the brain may mean something else entirely than activation in another part of the brain. This is like a broken record to know because I've been saying that a bunch of times now. But I feel like this could be interesting in that sense, because we should interpret like functional activity in, for example, the amygdala differently than we do in the prefrontal cortex, obviously. And with convolutions, because it's like translation invariant, you don't take that into account sometimes.
Yeah, I think there's lots of reasons to potentially get away from convolutions. Neuroimaging, privacy as well potentially is one for our distributed algorithms. Not that I'm convinced that MLP mixers will necessarily solve that, but I've been kind of thinking about them, and I think they might actually.
Yeah, they're also translation invariant, by the way. So
yeah.
Okay. Next one by Kevin, explicit input patches in vision.
Yeah,
Okay,
so this sort of talks about some of the same things, because really I feel like 2021 did a lot of just, hey, there's a lot of patches, well, a lot of work with transformers, which necessarily worked on input patches for vision, which then like did a bunch of different things with it. This is just one paper, which is the first time the first time autoencoders worked again in terms of getting better classification performance as a semi-supervised method over the recent ones, where You feed in explicit patches, you mask about 75% of them as the encoder, and then the decoder predicts out, and then you get a very good result out of a transformer architecture. I mean, this stuff has been done a lot before with Jigsaw. I could just cut mix, et cetera, et cetera. Like, I feel like this year was the year of like, let's take a look at how we can use an image and cut it up into, well, and see how the input really affects our results a lot more, rather than the, and maybe I'm wrong, but like the base architecture transformer or attention mechanism is less interesting than like the results that you see out of the large decision to do input patches or to change or to do contrastive with different inputs or etc. to me.
I don't know if Alex is on the call, but autoencoder in Alex's work also shows good performance, and it's not transformer based on downstream tasks. I'm just reacting to your statement there that it's the first time that autoencoder shows better performance with semi-supervised methods, right?
Yeah, I mean, at least in the computer vision literature, like usually it's all been about like the other sort of semi-supervised methods and not like the autoencoder recently. And it's nice to see that it works again, and it's nice to see that like generally, and it's also interesting to see that the rise of patches, I guess, which I think a number of slides here came into that discussion.
Thanks. Any comments?
It makes me, reminds me of BERT.
What's up?
It reminds me of BERT.
Oh yeah, it is very similar to BERT and like Electra and all these things. Like BERT, Electra, and like the most recent one, DataVec or whatever, they all mask, or they all take a patch and mask it, and like you might not mask as many patches, but it's all very, very similar. Yeah.
Okay, thank you, Kevin.
Swine transformers, that's basically, so this, I've been working with VIT and VIT offshoots in my research, and basically, like one thing I've noticed in like basically without changing the loss or the training methodology, like just moving from MLB to CNN and then from CNN to transformer, it seems like every time I get a what I would consider a more advanced model, there's accuracy improvement, which to me seems like architectures will be extremely helpful in solving a lot of real world problems. And this paper basically starts off by saying, kind of giving a small critique of VIT, that it's beginning like it's slightly more advanced than the NLP origins of transformer, and that like adding better inductive biases for computer vision problems is important. And so it basically, as far as I remember, attempts to replace like some of the self-attention with some more advanced something called shifted window, and it also merges like there's like a merge step after each layer, and they end up with fairly good results. It would be in my problem. I'm considering trying this if I can like locate the code, which this is from Microsoft Research, and they also publish the code. So basically, I have a bias towards like model improvements being a means to solving my problem. So that's why I was interested in this. That's it.
Okay, thank you, Bill. Any comments, any concerns with
Seems like patches are here to stay. We've had 3 papers in a row.
I probably should have chose a different one, but I didn't see all 3 papers, I guess.
Well, maybe it's just a fad of 2021, and then no one remembers this one hit, like one day wonder, like patches. What? That's ancient 2021.
Yeah.
It sort of mimics like some of the inductive bias at CNN, but allows you like that with like some of the global perceptive field perks of transformers. So
You can do that with CNN with properly connecting the
Routing.
neurons within the layer and stuff.
and it also reduces computational complexity. I think this went from like quadratic complexity on the image input size to linear. So there's some speed improvements on this model as well.
Yeah, that's great. Okay, let's go next.
Yeah, that's from me.
Okay.
So yeah, the paper is liquid neural networks, but that's not the official name, but that's how it goes by. The official name is liquid time constant network. It's an upgrade on neural ODE. When you're in neural ODE, what they do is that instead of your model parameterizing the hidden state, it parameterizes the derivative of the hidden state. So HT plus, like in RNN, HT plus 1 is equal to HT, some function of HT. But over here, it's the derivative of H is the function which your model is learning. But it was theoretically very good, but did not lead to did not beat the state of the art. So what this paper did is that they brought the same concept not only to the nodes, but also to the edges. And in this paper, they call it, they say that it's mimicking the synapses in the brain. So that's the idea. And now it does beat state of the art. So yeah, it was very interesting to me because they also solved the problem of irregularly sampled data, because once you're not learning the hidden dimension, but the derivative of hidden dimensions, it gives you more freedom. So because I was looking into things which can solve irregularly sampled data in time domain, so it works very good on that. And then they also show that it has more expressivity, and they measure the expressivity by the arc length. So the figure on the top right, if you have a bunch of MLPs and you input a circle, so at each layer, the expressivity of the output increases, and then they measure the arc length, and they show that their model is more expressive than traditional MLP or other models. And then they basically they do it on autonomous driving, self-driving, and on the bottom right figure, they show that CNN also work, but if you see, you can't see it clearly, but bottom right figure, the left one is CNN, and it focuses on the edges of the road. So it stays in the lane by just looking at the edges where the road is ending. But that's not how humans drive. You look on the road, on the horizon of the road, which their model does, which is the far right one in the bottom. And it's also more robust to noise. The noise is not in training data, because it's even in the testing data, it's calculating the derivatives and not just the hidden state. So they call it liquid because it's all like it's learning on the test data in some ways also because of the derivatives. Yeah, so it was very interesting to me. It's from MIT. They have already published like 3 papers, NeurIPS and Triple AI. So I don't know if it's just the work or because it is from MIT, but they're getting some success on it.
I think they also had like 16 neurons, right, for the autonomous driving.
Yeah, and yeah, one major other thing is that if they have far few less parameters than other and they beat state of the art by using far less parameters in their network.
Yeah, that's interesting. So alternative approaches, but liquid state machines and things like that, they were around for quite a while.
Yeah,
so-
the idea is not something very new. They just brought it from neural OD, it was in 2018. So they just brought the idea from the nodes to the edges also.
I also think that one big thing that they did in their paper, or at least that's what they do in the paper, is like they prove that it's like a dynamic causal model.
Yeah,
That's like one of
Because
the big
the-
things in their paper, is like 2 pages or something.
yeah, the figure on the top left, the right side, which is their model, they show that it's very similar to the the paper from Carl Christian, dynamic causal modeling. So they show that it's very similar to that, and they talk about dynamics and causality. So it's very interesting, at least on the paper, it was very interesting. So still have to see how practical is that.
But I think that also helped them publish it, although they also agree that they say themselves that it's not per se new ideas as much.
Okay, yeah, well, that's interesting to explore new ideas rather than incrementally improving the same transformer until somebody else publishes.
Yeah, I think it's
Conformer, and then we incrementally improve something. And then
it's just a mixture of RNN, neural OD, and transformer in a way. I think they combine because the edges thing, they took it from transformer, self-attention, and then learning the derivatives instead of the hidden dimension that was already in neural OD. So it's like a mixture of three things.
yeah, well, with some people claim we think by analogies and analogies only, and mixing existing ideas is the only thing that we do. So the art is to mix ideas that nobody sees that are mixable. So
MLP mixer.
yeah, MLP will mix ideas for us. Okay, TJ, that's your turn.
Yeah, so this paper's coming out of Danny Bassett's lab. Here they are trying to propose that information travels or triggers a signal propagation, which travels along the structural connectome of the brain and induces the change. And then they're looking at the change between the states and how potentially the state energetics transfer between them. They look at 7 different task fMRIs. But here they show that social activity shows a significant higher information content than all other tasks, where gambling and emotional tasks show lower informational content. They did a skew analysis that investigates energy requirements from high informational states, which then they showed that high informational states like the social task require higher energy to drive the brain into these states. And so here they're using information theory and control theory to look at how sensitive the task differences are along the brain regions, and could use as pivotal assumptions for understanding different dynamics and dysfunctions with psychopathology. There's a lot in the paper, so I don't want to drag upon it too much, but then I also added 6 other papers with notes in the slide deck if you're curious about them, but I thought these were some of the big papers. William already mentioned Swin RL, that's the ICML paper. Reward is enough, that's a big one from DeepMind, and just the thinking of like 4 pivotal people in the reinforcement learning community, and then a couple on data sets, and then I thought the last one, Fruit Flies Can Learn Word Embeddings, was just interesting to think about, and how you can learn context with small embeddings.
That was quick and very dense.
Oh, sorry about that.
Okay, thanks. Yeah, the extra papers is interesting. So that's how to hack one idea at a time. You add all of them on the same slide. Yeah,
I didn't know how many.
Yeah. So,
yeah, I didn't know if we. Go ahead.
No, like you kind of went. I kind of missed the main idea of that main paper. The information content of brain states is explained by structural constraints. What do they mean by structural constraints on state energetics? Is it in any way related to, is it abstract or related to somehow structural organization of the human brain network?
How the functional activity can flow through the brain, right? That's like the idea. Like you could, like there's like a constraint on how energy can go through the brain because of the structural organization.
Structural organization is anatomical structural
Yeah,
organization.
limits.
Yes. Yeah, so basically they're showing that more information has higher energy states, or more information that is needed for the brain state in a hierarchical order has different amounts of energy used. And they showed that gambling and emotions have a low energetic state, whereas social tasks have higher energy states.
And that is explained by how they're wired through the brain, right? It's like.
Yeah, but then they also look at the hypothesis and whether or not these social tasks are more spatially conserved, or whether or not they are more spaced out in the brain.
Yeah, exactly. Yeah, that's
Mhm.
what I meant by how they're wired. Like, those things are farther apart, so they need more energy because minimize wiring is the brain's mantra. I'm just kidding. But like,
Yeah,
if it's further away, it takes more energy, obviously.
yeah.
Okay, but there are some, like lots of axonal connections. There is another paper that's interesting that could fall into this list, but I don't
Okay.
know if it's already there. Where I think Allen Institute, maybe it's from Allen Institute where they imaged the individual neurons, and basically a mouse, I remember, and some other animals. But one neuron spans the whole brain with the connections. It's not like, oh, I see it here in the cortex and I just connect somewhere downstream, but it's like, it practically spans everything. It has dendrites very far away and axons. So
That's interesting.
that's, yeah, I found that interesting too. So it's not like, oh, okay, the topographical, or how do you say, the geodesic space of the brain is not like, okay, front and back, that means they're far away.
Yeah.
So,
No,
I
for
don't
sure,
know.
yeah. But I
It's
mean,
just-
going through axons, for example, takes way more energy than doing local neuron, like from neuron to neuron activity, because it's passive.
Okay, yeah,
Through axons is like active, like,
yeah.
It takes
you
more
have
energy,
to,
yeah. doesn't mean that it's per se like super far away, so it could be less energy. It could be like some connections will be more energy through axons and some will be less through axons. But obviously, if you're just super local, that is even less energy, because then it's just purely passive. And you can do with chemical and like electric.
Electric, yeah, charges and stuff, but how did they measure? How do we know how brain is organized? I mean, only recently, like I saw a paper that where we finally learning how brain is somewhat organized.
No, for sure, but I mean, maybe DTI or something. That's also what I think Ambridge shared a paper on function through structure or something, where they also looked at that. Like
Yeah,
they simulated the
DTI.
brain with like DTI connections,
Yeah,
which I guess is currently the best sort of like thing we have, apart from like making the actual connectome of the brain.
well, that's what Alan Institute is doing through histology and connecting it back and like seeing the actual, at least for small
It's actually-
animals.
Cambridge actually has the whole brain of a fly now, I think. Like they've done, they've like now like labeled every neuron and whatever and every axon and connection. It's actually interesting because they found new neurons even now, which is pretty wild.
Well, this year we found a new artery in human body, right?
Oh, wow.
So it happens. The evolution is ongoing, so, yeah. Okay, thank you, TJ.
Yeah, no worries.
Yeah, that's it.
Yeah, thank you. Actually, I was trying to read some papers for improved deep learning interpretability throughout the years, and I found some papers interesting. One of them is in line with model agnostic approaches, and another one is in line with model sensitive approaches. So I was a bit confused that which one to include. So first of all, I thought that I would include model agnostic approach, but later on I actually discarded that decision because I am not working in that line, because I'm trying model sensitive approaches. So, but I want to tell something, if anyone is interested about model agnostic approaches, there is a paper recently published in New Leaves 2021. The title of that paper, I didn't include it here, is actually they have tried to improve the line and kernel shape, because the line and kernel shape have the inherent problem that if you run the interpretability, if you run for post hoc explanations multiple times, they will give different results at different times. And the results can vary entirely because of the permutation nature. So the new paper has addressed these concerns. They have tried to associate some confidence on the attributions being computed. And they have named the new approaches as Bayesian line and Bayesian kernel share. So what they are doing is, I'm not going into the theory because I didn't read in detail, but their main goal is to associate confidence with the attribution. And their new approaches are assigning at least 95% confidence to the attributions they are giving. That means the attributions will not vary a lot if they run multiple times, like Lime or general kernel shell.
So they still sample though from a distribution, the way Lime.
I didn't read it a lot, but the main idea is they are associating confidence and they have ensured that the attributions will be at least 95% confident.
Okay, and so it's not unique, it's just mostly unique kind of thing?
Yeah, yeah, but unlike Lime and share, kernel share, for example, if you run Lime and kernel share, then if you run it multiple times, the attributions will vary significantly. And it may vary a lot. So
Even for Lime and Shell.
Yes.
yeah, that is what I'm saying.
If you.
And that's
use-
why they proposed Bayesian Lime and Bayesian share, Bayesian kernel share. So that will reduce the range of attributions and boost the confidence.
Also, Bayesian means add some priors.
In Lime and kernel shell, if you use infinite samples, then they'll be unique.
It's only n factorial, yeah. You don't need an infinite.
It's,
So I didn't include that idea here because I'm not working in line with model agnostic approaches. I'm working in line with model sensitive approaches. So-
Maybe in the future.
So this paper is based on model sensitive approaches. They have tried to incorporate saliency during deep learning training process so that they can get improved interpretability for post hoc explanation. So what they did is they computed saliency. It can be any kind of saliency during training processes. It can be raw gradient or it can be integrated gradient or any kind of
In the beginning or every iteration or?
every iteration.
Every iteration.
So every iteration you will forward pass, then you will have your traditional loss, and then you will compute saliency. It can be integrated gradients or vanilla gradient or anything. Then based on that gradient, what you will try to do is you will identify some features that are not informative. You will reject those uninformative
In the
features
image.
from the image, and then you will again pass another forward pass. Again,
Yes, so for those who don't know what saliency means, basically you have X, you have F, X is your input, F is your function, and you have some loss. And usually we compute gradient of parameters of F. In this case, let's look at dAF by dx, just practically dF by dx or dL by dx, loss on F, blah, 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 but on the X. So look at the gradient with respect to input and suppress something, mask out.
suppress the uninformative features, uninformative gradients, low values gradients, suppress them.
what does suppress mean? Is it like a
Suppress
full
means
binary
mask
mask?
them,
It's
just
it's
mask them,
binary mask.
replace them with zeros.
Binary mask or Gaussian mask or
Replace them with zeros.
binary mask.
So replace them on informative gradients by zeros and then make a forward pass again. So we will get two distributions. One is with the original input. That means the probability distributions with the original input and the probability distributions with the masked input. And then compute their KL divergence between these two distributions. So the loss will be the traditional loss plus the KL divergence and then back probability.
Did they talk about why they use the binary mask as opposed to other possible masks?
No, they didn't explain it in detail. Maybe, yeah, we can try out different distributions like, as you said, the Gaussian distributions or the mean value of the data.
That's-
Yeah.
So they're getting rid of noise, basically.
Yes,
Like
yes.
their gradients
During
are-
the training process.
Yeah.
And they have shown the left-hand side result shows the raw results. So the red line is the random baseline. So forget about that. The middle highlighted black line is without saliency guided training. That is the traditional training. So if they use saliency guided training, then it improves the interpretability. That means, yeah, it drops very sharply.
How do they quantify? Like, what does it mean for them to have better interpretability?
Because as you can
Or
see,
gradients, I guess, basically.
Is that how they?
The DAF by DX, DL by DX, with respect to data.
Okay. Well, what was the exact metric?
or what?
For defining the quality of interpretability?
So first of all, they tried two things, as I could understand. That is, they evaluated their approach with ROAR method, ROAR validation technique. So in ROAR validation technique, as you can see on the left, that when they use saliency guided training, the performance drops more sharply than the traditional training.
We should actually accelerate a little.
Yes.
We can talk about it offline.
Yeah.
And another thing.
I didn't realize that we have 4 more ideas to discuss in the last 15 minutes or 14, 13.
Yeah, I can finish it. And if we just look at the right-hand side box plot, yeah. So they are showing that they are creating gaps between informative and informative features. So the red is more wide and the outliers are actually informative features. So now the two sides of the informative features, positive and negative, are falling apart from each other. Yeah. But with the traditional approaches, the left-hand side of the box plot, the gap is very narrow. That means they are very close. They are not very apart from each other.
Okay, we took very relaxed pace. I'm sorry, I blame myself for that. Marina, thank you very much.
I'm sorry for getting that.
I mean, not with everyone. I thought, 5, 10 minutes, but no. Okay, Marina, can you tell me what to do? Videos, should I run it? Tell me when.
Right. So I'll just try to like, I'll try to like summarize the whole thing because like I don't think I can explain everything in this, and that's not the point also here. So there are like 2 papers which I found really interesting, and with one of them is this Dino, and the next one is this Codex, which is in the next slide. So Dino is like it's like a paper which was published by FAIR, and I think I really found this interesting because like this is like so what they're trying to do is in a very vague way is that if you can just play the video. So as a human, I'll interpret the dog as like the main subject as the dog in this video that will be running on that field. And I mean that's really interesting because that's exactly like how we behave. But and I mean this is going to be really great coming ahead for further research as well. So you can do the segmentation part as well. I'll just quickly like explain the architecture in this. So as you can see, so what they try to do is they basically try to interpret the method as self-distillation method with no labels. And so the teacher here is the distillation part. And so what it's going to do is that, so basically the teacher will be learning everything and then you will have the centering of this and you'll also be the sharpening the whole, the whole mask of it. And then you will also give this whatever input or whatever output of that model is, you want that model to be just similar to student. And so student will again train that model and give like it will do the exponential moving average on the teacher. And then like you want you want the teacher and the student to have this kind of the same model, but that's how it learns. And I think that's I won't be going too much depth into it right now. Yeah, I mean, this is like one of the papers which I found really interesting. One thing which I found really interesting was the softmax which they're using in this, because normally you want softmax to like normalize the distribution, but after softmax, they're also uh, yeah, so they're also using cross entropy. Yeah, so they're using cross entropy after softmax, which is like really interesting, because like after that you're basically making a distribution since you have no labels and no classes. So you're making that classes automatically by using that cross entropy, and you want that probability for each and every class, and that's how you're basically selecting the actual object in that image or that video. So that was really interesting for me, and yeah.
Okay, thank you, Renal. Was there a second paper you mentioned, you said?
Yeah, it's in the next slide.
Okay.
Yeah, this is like I fell in love with this paper. So I presented this paper before also, but I'll just quickly give a glance. So this is basically the backbone of GitHub Copilot that came this last year. And the main thing about this is that they are basically trying to evaluate each and every problem statement automatically by using large scale models like GPT-3 or GPT-J. And they want so like for example, left hand side, as you can see, there's a comment like you want the function of a INCR list to return the list with elements incremented by 1. And so the model will give you exactly that. It will give you that return I plus 1, blah blah blah. And so a very interesting part about this, two interesting part about this. First was that the evaluation part which they did, and something which is called like pass at K. So they use like human eval data set. Basically, the humans will be writing the test cases in order for the problem to be passed, and that is exactly what we as a developer we also do that. But for them to just do that, just to use those test cases to pass each and every problem statement, that was really interesting for me. And the second part, which is pass at K, it basically tells that for K is the number of problems here. So the number of problems which will be passing for that unit test will be the like what's the ratio of that. And in this case, for this model which they built, it was like really high. So that was really interesting. And in the right hand side, the graphs that we have, they have basically tried different large scale models for that, for NLPs. And the best one which worked was Codex S Oracle, which is like which is what they are using currently. Not currently, I think, but they were using for the GitHub Copilot. So yeah, I think these were the two papers which I found really interesting.
Okay, thanks, Renal. Let's leave the questions now to the end. I just hope we can, yeah.
You're looking at me specifically.
Yeah, but Mohammed, we can't hear you. Yeah, no sound from you. No. Can you try figuring out, and we'll come back to you, just in the interest of time. Sajad, towards causal representation learning.
Yeah, this is a paper from Joshua Benju's group. I think I updated this figure, but anyway. So if you remember when we had David wanna go mass suit first? I heard something.
If you have updated the figure, I want to give you the best figure.
Mm-hmm. No, I heard someone talking. Anyway, so if you remember when we had David having his talk about causality here, I asked him like, what is the next step in this field? And he said that it will be the integration of this field and machine learning So this is what this paper is talking about. Basically, they don't actually have any results. They don't do anything. They just set the grounds for what it means to integrate these two in each setting of machine learning, like what it means in transfer learning or augmentation or reinforcement learning. And it's a very long 16-page paper, and I think it's very interesting. For example, in this figure, if they like, we want to show that if we have a causal graph for this figure, and if we interfere with the node that is related to the finger of this robot, it will change the position, and it should happen in the image that the object fall. So I think it's very interesting, and I personally want to work on this direction later.
Thank you, Sajid. Let's again, pruning at initialization. That's probably yes.
Yeah. Hi. Yeah, so like last year, pruning at initialization was the concept that I found to be most interesting. Yeah. And yeah, and also like related to my research a lot. And two of the papers that really shaped and pruning at initialization, and SNP was the first one that that introduced the concept, although like the basis for this work was laid out by Yang LeCun in 1990, and all of this work is, all of these other works is kind of like based on top of that, and basically just kind of Taylor series approximation of the neural network loss function, and then like and doing tricks on how we could leverage that and use as a criterion for the weights of the neural network that would give some sort of score whether those weights are relevant to the task or not. So SNP was the paper like that shaped this this area in it was actually in 2020, if I'm not wrong, but I discovered it last year, and then I grasp build up on that. So SNP tries to keep the loss like stable while pruning the weights, while as grasp tries to maximize gradient flow through the network. Both has their like pros and cons, but like both were important in like proving that it's possible to prune neural networks even before like training just with like a simple mini batch. So I think it has like great potential like for future research, and also like recent research. Although these work are very important, but they actually do not result in wall clock efficiency increase. But a recent work like pixelated butterfly and some other block matrix representation of the neural network weights results in more efficient and more efficient training and sparse training. So I think it has like great potential for interesting research going forward. I think that's it.
Yeah, thanks, Riasat. One quick comment from me. Shameless plug for Riasat's work. His work is actually better than those two in the final result. And notice the fine marketing work at play. Pruning method. SNP didn't snip enough, so we had to grasp something, and we published the next paper to grasp something more that SNP was missing.
Like that the title?
SNP
doesn't snip enough.
No, that's not the title, but that's the implication. That's what they were like. Let's grasp some more. I mean, I find it ingenious. Okay, well, now Mohammed, can you try? Oops. Oh, yeah. So, well, this is some work from Farfalla. Let me go back. Wait. by design. Can you try talking, Mohammed?
Yeah. Can you hear me
Perfect.
now?
We can hear you.
Yeah.
Can you introduce your paper now?
Yeah, so concisely, this paper is about nuclear segmentation. When we have a microscopy image where this part actually is a challenge because we can find an overcrowded cells in this case. So if we look in the upper left, we can see these like 3 cells that actually have a challenge to segmenting them separately. So they have a method that here using like a unit network. So in this case, they are actually at 2 additional layers, one for finding the probability of pixels that these pixels are close to the center of the object. And this case actually, they actually found like a layer for that, and then another layer, they are trying to find the pixel, how far it from the boundary. And in this case, actually, they make like a 32 degree in each direction. They can find this probability, and they mix both together in order to find a polygon in the output. So the challenge actually comes from the beginning that if we are using the bounding box classical method to classify or segment in these cells, actually this will ended up with a huge overlap regions that can actually misclassify our cells. And in this case, actually, when we go to the non-maximum separation method, a lot of cells will be actually discarded when this shouldn't be happen. So what they are trying, the main idea is to not use this bounding box or something like that, but just they are trying to create a polygon. And this polygon should be actually in a star convex, so we can actually separate the cells that are very close to each other. And the results actually, they outperform the unit in the case. And what we are explaining now is the 2-dimensional, and the 3-dimensional actually is very close to this idea, just they add an extra, the 3rd dimension in this case, and get also a better result than any classical method that we have now.
Great, thank you. Thank you, Mohammed. We're actually
Thank you.
out of time, and of course, we didn't cover a lot of interesting ideas. Nerves were interesting this year. Paper by Pedro Dominguez, neural networks are just kernel classifiers was probably the best. There is other, in my view. And
I was gonna say, damn, just trump all this. Actually, there's this one paper that's the best, so, nobody brought it up, but,
yeah, exactly. That's what I was trying to do, but you caught me by my hand. Okay, well, lots of interesting ideas, and thanks for sharing. Let's do maybe this more often, every year, instead
Next year I'll
of
do one
once
year.
in 3 years, as this time. We didn't do it last years. So thanks everyone who joined, and I think we're done and can go on to our next meetings, which we are looking forward to.
Does anybody do anything other than meetings?
Yeah, exactly. Thanks. Bye-bye.
Bye.
Bye-bye.